Good day, my name is Mira Karinina from Nation Star Academy, Surabaya. I am presenting my research, the correlation of prevalence rate to the efficiency of number of COVID-19 swab tests using the pool test method. I work on this research to answer the research question: how efficient is a pool test if implemented in a population given their prevalence rate? This research is limited only to theoretical mathematics and not considering technical factors like reagent dilution or equipment accuracy. Let's begin with this tree. The notation M is for the stage and N is the pool number in that stage. In general, N max is 2 to the M minus 1. For the last stage, N max represents the number of samples N, and M represents the number of stage S. Now, let's examine the branch. Take this branch for example. The parent stage is M minus 1, and the parent's pool number is the half of the children's. If it's not an integer, then we round it up using the shielding notation. The value of IMN depends on its parent's value. I wrote this fact in a formula. If the parent test result is negative, then there are no children because no further tests are needed. If the parent test result is positive, then the children can be either 0 or 1. This formula is valid only if a node has a parent. For the top node that has no parent, the test result must be 0 or 1. That's for the test result. How about the number of tests? If test result is negative, then there are no tests in the next stage. But if it's positive, then it will be split into 2 tests. For a complete tree, we sum up this function for each node in a stage, from the first stage until the second last stage. That reflects the number of tests in the second stage until the last stage, because the function counts the number of tests conducted in the next stage. Then we add 1 for the top node. Simulating it in a spreadsheet, here's the results for every possible combinations. P is the number of positive samples and T is the number of tests. Now, let's calculate the average number of tests. First, I recap the previous table. For example, there are 2 rows where 2 positives need 5 tests and 4 rows where 2 positives need 7 tests. The total is 6 and the average is 2 times 5 plus 4 times 7 divided by 6 equals to 6.33. Here's the complete table. And now we can draw a line chart. Juan Dluvoch in his blog wrote that the worst case scenario for 2 positive samples is 1 over 6. But my table shows it's 4 over 6. I contacted him by email, and here's the explanation. There are 4 splitting possibilities. If the parent node is 0, then no further tests are conducted. But if the parent node is 1, there are 3 possibilities. If the left node is 1, then the right node can be either 0 or 1. But if the left node is 0, then we don't need to test the right node anymore, because we know for sure that it must be 1. Now we need to modify the formula. The previous formula is now valid for the left node only. For the right node, we add conditions for its left sibling node. We also add a formula for that eliminated node. There is 1 test eliminated that only happens where the parent is 1 and the left sibling node is 0. So the number of tests in a tree is now. Here's the simulation table, the recap, and the line chart compared to the previous non-optimized formula. As we can see, the worst case scenario for 2 positive samples is now 1 over 6. In a regular test method, if we have 4 samples, we must conduct 4 individual tests. We can only call a pool test efficient if the number of tests is less than 4. We can see here, only 1 out of 16 possible combinations is efficient. Does that mean that the pool test is inefficient? If you flip a coin, there are 50-50 chance of head or tail. If we flip 2 coins, the probability is distributed evenly. Recap, there is 1 chance of no heads, 2 chances of 1 head, and 1 chance of 2 heads. The pool test is different because it's not always 50-50. This is where the prevalence rate comes in. The prevalence rate is the number of the infected persons in a population. Say it's 10%, then the probability of positive sample is only 10% and a negative is 90%. The distribution is uneven. There are 81% chance that we have all negative samples. Applying that to 4 samples, the probability is like this. Suppose we test 40,000 samples. If we split them into 10,000 initial pools of 4 samples, then the expectations of the number of tests are, compared to 40,000 samples tested individually, it's 61% more efficient. For 8 samples in the initial pool, the efficiency is 0.63. For 16, it's 0.67. These are all assumed that the prevalence rate is 10%. By changing the prevalence rate variable in the spreadsheet, I summarize the efficiency for 4, 8, and 16 samples. We can see from the table that the efficiency is about 1 when the prevalence rate is 20%. It means if the percentage of infected person in the population is 20%, then the number of tests is about the same as individual tests. From this point up, the pool test method is no longer feasible. For the optimized version, that critical point is achieved if the prevalence rate is 25%, which is better. Now, let's implement the simulation on some real-world examples. Example number 1, country level. Qatar has the highest prevalence rate. It's 5.62%, far below the threshold of 20% or 25%. The efficiency is shown in the table. Example number 2, city level. The highest number of COVID-19 inpatient data in Surabaya is about 3,000 of roughly 3 million population, giving the prevalence rate of 0.1%. The efficiency is shown in the table. The last example, community level. 77 out of 2,200 means a prevalence rate of 3.5%. In this example, using initial samples of 4, there will be 550 sets of pool tests. Using the optimized method, the expectation will be approximately 810 tests. The efficiency is 0.37. If one swab test costs 900,000 rupiah, then we can expect a huge saving. From this research, I conclude that the lower the prevalence rate is, the more efficient the pool test will be. By using the prevalence rate data in a population, the decision maker can estimate how much time and cost could be saved by using pool tests. We can explore this research more in the future. For example, splitting the pool into more than 2 pools, splitting the pool into different number of pools, and comparing the binary split pool test with other pool test methods like two-level pooling or PURIM.